one extra days for assignment number 6. Okay, yeah. The other thing is I uploaded the formula sheet for the final exam. Not all the formula that you have seen yet, but you can take a look at it just to prepare accordingly. So it's fairly general formula sheet that you're going to see. Okay. I think you still need to understand each one of the formula, even though you do have the formula sheets here. Okay. Okay, good. So we have started the spherical coordinates in the previous lecture. Let's do a quick review at here. Basically, what spherical coordinates are, and then we'll look at a few examples of evaluating triple integral using spherical coordinates. So when you have a point P in 3D space, okay, you can basically use a set of new variables to describe the location point P, and we use rho phi theta, okay, to basically indicate this location of the point P here. The rho is defined as the distance from origin to the point P, and the phi is defined as the angle between the z-axis to where OP is. Okay, so phi has to be starting from the z-axis up to the OP. And then theta is basically when you drop this, project the P to xy coordinates, and that corresponding angle here is the theta from x-axis. Okay, so that's rho phi theta. You can easily find the relationship between x, y, z and rho phi theta. So x equal to rho times sine phi cosine theta, and y equal to rho sine phi sine theta, and z equal to rho cosine phi. Okay. Alright, so that's the connection here basically when you do substitution for x, y, z, and this is the formula for you to do the substitution at here. Okay. Now, in the previous lecture we also illustrated that if you have an equation or a surface or a 3D object or 3D equation, you can always transform that basically the equation from xy coordinates into rho phi theta spherical coordinates by using the substitution, the three formulas at here, three equations at here. Okay, yeah. So for example, we illustrated that if this is the sphere, this is definitely a sphere, but it's a sphere with the origin at 0, 0, 1, with a radius of 1, and with the substitution into here, you'll be able to get a much shorter equation, which is just rho equal to 2 cosine phi. So that is equivalent to description for the same sphere in 3D space at here. Okay, yeah. And the other example, when you have a cone at here, this is the cone equation, surface cone. Right? If you substitute the three formulas, three expressions to here, and you'll get phi equal to pi over 4, and that's basically same description for the same cone at here. Okay. So that type of things established basically whenever you have the same object, it can be described using a different set of the coordinate system, coordinate variables, right? But it's the same thing. So in terms of evaluation at here, what we're evaluating basically, here's the original evaluation at here. Okay. So this is the original one here, right? But we are not going to evaluate using x, y, z coordinates. We are going to evaluate the same integral here using rho phi theta, the spherical coordinates. Okay. So basically what we do is we replace the x with rho, basically with the three expression here, rho sine phi cosine theta, and replace the y with the rho sine phi sine theta. Replace the z with rho cosine phi. And dv originally it's dx, dy, dz, or any orders, right? But in terms of the new spherical coordinates, so we have d rho, d phi, and then d theta. Okay, so that's basically the new three variables here. However, right, we need to plug in a basically a scale at here. Okay, so the scale at here, if you recall that, we can use this so-called the determinant, the Jacobian, to find this scale at here. Okay, so let's calculate this guy at here. Okay, so what exactly is this determinant, the Jacobian, at here based on this transformation? Okay. So this is actually quite straightforward. Basically, if you recall that the Jacobian matrix, okay, is partial x over partial rho, partial x or partial phi, and then partial x, partial theta. So it's 3 by 3, partial y, partial rho, partial y, partial phi, partial theta, and then partial z, partial rho, partial z, partial phi, partial z, partial theta. So this is the Jacobian here. Okay, this is Jacobian matrix, and x, y, z are the expressions over here. So now you just have to take partial derivative x, right, with each one of the variables, and plugging into this each one of the partial derivatives here for the results. Then you calculate the determinant of this 3 by 3 matrix. Okay, so I'll leave that as exercise for yourself to do. So you calculate the determinant of this. As you will see that the determinants for this derivative, for this 3 by 3, will turn out to be just a rho square sine phi. Okay, so that's your determinant here. So if you look at this determinant here, and we need an absolute value for this determinant, right? So let's take a look at these results here. Rho square sine phi. What's the definition rho? Rho is the distance from origin to this point P. So naturally, the rho is always a positive number, right? And phi is an angle defined from the z-axis to the OP, basically the vector at here. And if you recall in the previous lecture, we specifically said the phi angle, right, is always between 0 and pi. So it's limited. It has to be, the minimum is always 0, the maximum is, it cannot be beyond these two numbers. So phi is always between 0 and pi. So then you look at this sine here. So when you have a sine, what's the sine curve is? This is sine curve here, right? So this is between 0 and pi. So for any value angle between 0 and pi, the sine angle is always what? Greater than 0. So basically, for this one here, you basically just replace this with this guy, right? Replace with this. Okay. So ultimately, your triple integral in the spherical coordinates, okay, essentially just become rho sine phi, d rho, d phi, and d theta. Okay, so that's your expression for evaluating the triple integral in spherical coordinates. Okay, yeah. In terms of, if you need to remember formula for evaluating triple integral in this is basically the formula here. Okay, yeah. So now the next question is. The next question basically is, given this triple integral, how do we find the limits for rho, the limits for phi, and the limits for the theta? Right. So that's basically the next step right here. We need to find the limits for the three spherical coordinates right here. Okay. You do have another option. Instead of using the Jacobian in here, you can also use a different approach, okay, to find this expression in here. Like will be listed over here. So you see that. So this one here. So you can also basically try to. never say yes. Yeah? You can also try to create a very small volume, okay, differential volume in the direction of the spherical coordinates axis, and then you find the small volume. So that small volume will be just basically rho square sine phi d rho d phi d theta. Okay, it's the same results if you as we use the Jacobian transformation basically. Okay, yeah. So take a look at this. Yeah. Actually, I saw a very good picture. Spherical coordinates, it's interesting coordinates. So this is an interesting graph using spherical coordinates right here. It's basically a regular type of surface. If you, this is the expression in here. If you change the coefficients at here, and you will basically get all different type of weird type of bumps, okay, and surface drawing at here, okay, yeah. So try it out. There is this neighborhood command in here for you to try it out. Literally, you can't draw that in the Cartesian coordinates, but you can draw that in spherical coordinates. Okay. Yeah. Okay. So what we're going to do is we're going to start from here to look for the limits for rho phi theta, and then I'll show you through an example right here how we can find the limits for rho phi theta. Okay. So let's do that through an example right here. So this example here basically asking us to find the volume of a ice cream cone. Okay. So what's this cone right here? I'll draw it for you. Okay. All right. So the ice cream cone is constructed by two different surfaces. Okay. One surface is it's a cone in here. So this is a cone basically. Okay, this is a cone here, and this cone is phi equal to pi over 3. Okay, so pi equal to phi over 3. And on the top of the cone, okay, it's covered basically by a whole lot of ice cream in here. Suppose that the boundary of the ice cream here is part of a sphere, and the radius of the sphere is rho equal to 1. Okay. So that's the object at here. So this is two pieces. One on the top is a part of the sphere, rho equal to 1, and the side is actual cone surface, phi equal to pi over 3. Okay. Yeah. Now if you recall that when you see phi equal to pi over 3, basically it's referred to this angle here, right? So this angle is phi equal to pi over 3 here. And in Cartesian coordinates, this is equivalent to say this is z equal to 1 over root 3 square root x squared plus y squared. But we don't need to use the Cartesian coordinates here, but just this is the connection, okay, from here to here. Okay, this is in spherical coordinates. This is in Cartesian coordinates. Of course, for the sphere, this is basically x squared plus y squared plus z squared equal to 1, right? Yeah, and that's equivalent to say rho equal to 1, okay, in the 3D space, okay, using spherical coordinates. Okay, now given this ice cream here, so this is basically your region D, right? This is your region D here, and we're trying to find the volume of this region D, okay, right here. So volume of region D basically means you integrate this, okay? So triple integral with the integrand, which is 1 at here, okay? So that should give us the volume. Now, obviously, we're not going to evaluate this thing using Cartesian coordinates, so we're going to evaluate this one using spherical coordinates. Okay, you can try Cartesian, but it probably will be very difficult. Okay, yeah. So here's the steps right here. First step, okay, basically for any type of these questions, sketch the region D. Okay, so always sketch out the region D. In this case, I sketch it for you. Maybe the question just gave you a description saying it's ice cream cone sandwiched by rho equal to 1 and phi equal to pi over 3. So you still need to be able to sketch this out, right? Sketch region D. Okay. So once we sketch out the region D, okay, step number 2, okay, is you need to draw the shadow of this region D, in XY plane. So why you have to do this step is because you need a shadow to find the theta limits, basically. So for example, in this case here, so we're going to draw the shadow. That's pretty obvious because the projection of this cone into the XY plane, you get a circle here, right? Which has this top edge at here. So that's the circle. Okay? Yeah. So we'll try to find. Actually, in this case here, we actually don't really need to know the radius of the circle, okay? Because in this case, the shadow will only be used to find the theta limits. Okay? So the radius of the circle is actually not important in this case here. But we do just need to know what the shadow looks like at here. Okay. So draw the shadow in this XY plane at here, okay. And then you will start to looking for the limits now. So find the limits. Let's say first we'll find the rho limits. Okay. So to find the rho limits, here's what you do. Starting from the origin, okay. Starting from origin, you draw a reading lines in the direction of the rho axis. Basically, starting from origin, you draw a reading line out of this region D. Okay, so that's your first step at here. So draw a reading line, okay, from origin through the region D. Okay. So basically, the drawing direction, the reading line direction is in the rho axis direction. Okay. Yeah. So from here, out of this region D, then there will be always a first contact and the second contact. So in this case here, the first contact is right at the origin, and the second contact is right on the top of this cone at here, right? The cone surface. So the first contact, as usual, the first contact give you rho mean, second contact give you the rho max. Okay? Yeah. So that's basically first contact give you the rho mean, and second contact give you the rho max. Okay. So this is where you have to look at the rho mean, rho max. In this case, rho mean is definitely 0, right? It's right at the beginning. Now rho max is sometimes you have to be careful. Basically, let's say if you draw it here, draw it there, right? So is there any a difference in terms of the rho max? But you have to know that exactly that this distance from here to here, right? This is your rho max at here. Okay, this is your rho max. So no matter where you draw, it's an arbitrary sketch at here. But in this case, it's quite straightforward because really wherever you draw that reading line, it always lands at the top cone surface. And top cone surface, as we just said, it's part of the sphere. So the rho max in this case equal to 1, right? Equal to 1. Okay. So that rho max equal to 1 in here. Good. And now let's find the phi limit. Phi limits. For the phi limits, so here's what you do. Okay. So you basically, so let's see. Here is the drawing at here, right? This is the drawing, the reading line we draw here. So you will start from the z-axis, okay? Start from the z-axis, always start from z-axis. And then sweep these reading lines all the way across this region D. Find the two edges that sandwich this region D at here, okay? So in this case, you see I start from the z-axis. So when you start here, you're already within the region D, so that basically is one edge, right? You can't start anywhere else. You had to start from the z-axis, right? That's how the phi angle is defined. Then you keep sweeping, so the other edge is where? It's right here, isn't it, right? The other edge is right here. So basically, you get one edge over here, and one edge over here, okay? Yeah. So, and now I can try to find the phi limits now. So for the first one here, the phi angle is always angle from the z-axis to that reading line. So phi mean is basically equal to 0, right? And the phi max is right on this edge at here. And that edge is corresponding to what number? Pi over 3, okay? Yeah. So that basically the second here. So basically what you do is you sweep the reading line, okay, from z-axis, okay, to, okay, from the z-axis cross the region D. Okay. The two edges, okay. Now in this case, the first edge corresponding to phi equals, not necessarily. Sometimes your phi may be your first edge maybe is on 30 degree. Who knows, right? It really depends on the actual region D there. The two edges gives a phi mean and a phi max. So in this case, your phi mean is 0, and your phi max is pi over 3. Good. So that's your phi limits here. Okay, so that's how you find the phi. And last, theta limits. So theta limits basically as the same process you did for polar, for the cylindrical. You draw a reading line out of origin in the xy plane. Then you sweep through this shadow here. Right? This is your shadow. Okay, this is your shadow. Sweep the shadow and find the total theta angle, right, covering this shadow. So in this case, the shadow is a whole disk. So the theta limits basically starting from 0 degree and up to 2 pi degree at here. Okay. So that's your last step. Find theta limit. Okay. Sweep through the shadow and find theta mean and theta max. So theta mean is 0 and theta max is pi over 2 pi. So that basically finish the process of finding the limits for the three variables here. Okay. Yeah. So before we move on in here, so let me emphasize again the process. Basically, I think I emphasized this when we talk about double integrals and also triple integrals in other two type of coordinate systems. It's about, this is integration. So this is about sweeping through the region of integration. So what's the region? Region is a D here, right? So you're sweeping through or regenerating this region D. So you look at this one here. The first step is what? The first step, we basically created a line segments here, right? That's your first step, sweeping in this rho direction. Second step, sweeping in the phi direction. So technically speaking, you're starting here, you sweep all the way, okay, up to this location. So you created a part of the, like a pizza shape at here, right? Yeah, that's the second sweep. Then you create a cross section. The last sweep is to sweep this a cross section across this whole shadow is which is a 360 degree. So you can imagine you basically recreated this region D at here, right? Yeah. So no redundancy, and covering every corners of this region D, right, by doing these 3 steps at here. Okay. Yeah. So now you can lay down the setup for the triple integral at here. So we're talking about the volume at here. Basically, originally just a dV. Okay. So now we are going to use spherical coordinates. So dV originally is the dx, dy, dz, but now it changed to rho square sine phi, d rho, d phi, and d theta. Right. And the first limit is rho. Rho is 0 to 1. Second limit is phi is 0 to pi over 3. And last, the limit is theta is rho to 2 pi. Okay. So that's the expression, the setup for this triple integral. And then you can calculate this triple integral one by one from inside to the outside. It should be a very straightforward integral right here. There's really no trick, and then you will be able to get which is pi over 3. Okay, yeah, so it should be very straightforward. So practice yourself. Okay. So the important part is basically you, if you're asked to evaluate in spherical coordinates, the important part is to follow the procedures and find the limits properly, right? Find the limits properly here. So, before, any questions so far? Okay, yeah. Now, before we move on here, I need to wrap up a loose end. Now, if you remember, at the beginning, we said the phi has to be between 0 and the pi at here, right? So phi cannot go beyond this these limits, this 0 to pi limits here. But why, right? Okay, why doesn't have to be limited between? Yes. Pardon me? Oh, yeah. Is that good? Yeah. So why this phi has to be between 0 to pi according to this whole definition here? So here's a simple answer. I wanted to think in terms of scanning process, right? Scanning process we did. Okay. So let's see. Let's say I want you to create a sphere. Okay. So let's see now your task is to create a sphere using any software, CAD software here, right? Yeah. So what's the step I want you to how do you create this one here? So the step is first you can create a sort of a line segment set here, right? And then second, what do you create? You can create a half circle at here, right? And half a circle at here. And then in any CAD software, then what do? You can basically sweep this cross section from 0 to 2 pi, right? You create this this sphere here, solid objects. So what if the second step? Look at the second step here, right? The second step is the first line segment. How do you create this the half circle? You go from 0 to how much? To pi, right? To pi. So what if you go from 0 to, instead of 0 to pi, go from 0 to 2 pi? Then imagine what would you generate now? You generate a circle now, right? A circle. Now you can go back and then try use your SolidWorks. If you draw a circle and then you draw an axis and then you ask to do a sweep of this circle around the axis, guess what's going to happen? The SolidWorks actually will pop up an error message. I forgot exactly what that error message is now, but it's something to do with redundancy, basically. Okay? Yeah. And of course, you can argue, okay, instead of sweeping this 360 degrees, you can sweep this circle by how much to generate this circle? 180, right? Yes, absolutely, no problem at all. However, this is about the mass that here. It's not really about just to generate the sphere. So if everybody agrees to what we just said, instead of a 0 to pi, let's do 0 to 2 pi. And then the theta angle, instead of 0 to 2 pi, and make it 0 to 2 pi. Right? If everybody agrees, that's fine. But unfortunately, that's not everybody agrees. Everybody agrees now is this. Okay? So that's why the theta, the phi angle here is limited to a maximum pi and a minimum of 0 degree at here. Is that clear? Yeah, okay. So there's one little thing here before we wrap up this triple integral here. Just like a double integral, okay, we have a number of applications associated with the triple integral. It's just one natural, basically, transition or step forward from this double integral to triple integral here. Okay, as you're gonna see, a lot of the formulas I write down are pretty much just adding one integral. Okay, yeah, for the application set here. So I'm going to write down a few at here, and I will only give one example. Okay, but you probably will see it's pretty much just basically talking about the same thing here. First, we can use triple integral to calculate the mass of a 3D object. Okay. So we can let's say, a function delta xyz representing the density. Okay. Then the mass for any region D is basically, it's the density, okay, times the dv here. So that'll give you the total mass. Okay, total mass of the 3D object. I mean, if you this is a triple integral. If you get rid of one integral, right, and of course you're gonna get rid of one variable here, then it'll be xy, and instead of dv it'll be dA. Then you get the mass of a thin plate, right? Yeah. So as a matter of fact, the formula is written at here. This is actually a much more general formula, because the formula here describes the properties for a 3D object set here, right? Instead of just a thin plate. The thin plate really, it's not an actual thing, right? Yeah. And another thing is what we call average value of this function f of x, y, z, okay, in region D. Average value of this function in region D. This is basically the formula, if you recall that. Okay, the volume of D, and then triple integral, integrating this function f x, y, z, okay, over the region D. So that will give you the average value of this one in region D. For example, if this represents the temperature distribution, for example, inside this classroom, and what's the average temperature distribution, average temperature inside this classroom, then you plug this temperature function at here, and then you calculate, of course, the total volume of the classroom. Okay, then this triple integral divided by that number, then you get the average temperature value. Okay, yeah, that's the average value. There's another average concept called the weighted average. Okay, the weighted average. We often in time we can weight the average using the density function. You can use basically any functions to weight, of course. So the weighted average f, okay, instead of the 1 over volume, it will be the 1 over the mass. And then you have this original function f at here, the weighted average f at here, okay? And then time the density function, for example, the delta x, y, z, and dv. Okay. So that's the weighted average. If you remember, basically this portion here is the weight. You're weighting the function f, okay, with this number here, or this function here. So that's a weighted average. Very similar, just by increasing the integral from 2 to 3. So another useful one is a center of mass. X bar, Y bar, Z bar, where the center of mass is for an arbitrary 3D object. So X bar equal to 1 over the mass, triple integral over d, x times the density, and dV. That's your X bar. Now similarly, you can find your Y bar is 1 over the mass, y times delta xyz dV. And Z bar, of course, it's the same thing. Now all of this, you will have the formula in your formula sheet for the final exam, right? If you know one, you pretty much know the other one for the center of mass. That's your center of mass. Okay. You can easily derive the center of mass from this weighted average function formula right here. And the last one is the moment inertia. Okay, so moment inertia right here. So this is actually the true moment inertia now. This is the moment inertia for 3D objects in 3D space about certain axes. So moment inertia. The general formula for moment inertia is this. Moment inertia basically is the distance to the rotation axis square, and then delta function, the density function, and dV. So this is the general formula. So you take, for example, take one small mass, right? One small mass. This is one small mass right here. Time the distance square. The distance is how far is it to the rotational axis. So this small mass times the distance square, then you add all of them up or integrate, and you get a total basically moment inertia, right? So this is one single. This one here is just representing the point mass moment inertia, and when you add them up, you get the moment inertia for the whole object set here. Okay. There are a few special moment inertia, of course. For example, the first one here is the moment inertia about z-axis. Okay, about z-axis here. So here is what I mean in here. Let's say I have a 3D object. Okay, so there's 3D objects here, represented by region D. Okay, so this object is represented by a certain region D with a density distribution, for example, delta xyz. Okay. Now we're interested in the moment inertia of this object with respect to the z-axis here. Okay, z-axis. So technically speaking, what you do is you can literally just pick a small point mass, okay, anywhere inside this region D, and then you basically find the distance from the small mass to the z-axis. So then, right, and then take a square of that and multiply by this and do the triple integral. Okay. So for any point, basically this is a point, this is a point. For any point in the 3D space to the z-axis. So this portion in here, this is, let's say if this is D here, that distance is actually basically equal to square root x squared plus y squared. Okay, so that's the distance. So basically your moment inertia at here is what? It's the square of this, which is x squared plus y squared now. and then time delta xyz and dv. Okay, so that's the how you can get this moment inertia here. So we typically write Iz to represent this moment inertia here. Yes. It's a 3D, right? So my drawing is a little misleading. I mean, if you pick from this point here, right, it'll be this distance, right? Yeah. So basically, think about there's a coordinate system. You're right here to that vertical line. That's your distance from this point to that axis, right? Yeah. So it's not just the y, right? It's actually square root x squared plus y squared. You can drop this point basically to the xy coordinate system. So when you drop this point over here, this is your x, this is your y, right? So from here to here, that's your distance. Okay. Yeah. Is that good? Yeah. So I want you to maybe try it. What's the moment inertia about the x-axis, for example? Okay. What's the moment inertia about about the x-axis? So about the z-axis is x squared plus y squared. And you can take a wild guess. If it's about the x-axis, this got to be y squared plus y squared. Y squared plus z squared. Yeah. Okay. And similarly, the moment inertia about the y-axis will be x squared plus z squared. Okay, like this. Okay, so that's the moment inertia at here. Okay, the moment inertia. Yeah. And often in time, if you look at tables, they often in time will give you some very special moment inertia for a 3D object. Okay. Okay, so let's take a look at example here, okay, and then we can wrap up this triple integral. So the last example will be on applications of the triple integral. I'll give you an object as shown below here. So the object is given as this. The object is basically it's a cone. Okay, it's a solid cone. So the cone here is between z equal to a x squared plus y squared. Okay, that's the cone in here, right? And then the cone is capped by a plane on the top, z equal to b. So the value here basically on the top here is the z equal to b. So it's cut off by the top plane. In other words, basically the top coordinates that are here is b. So that's the object, and we wanted to calculate and assume, and also assume that the cone has a density distribution, a constant 1. Okay? So it's evenly distributed, and we want to calculate what is the moment inertia Iz for this cone right here. Okay. So if you try to spin this object around this z-axis, it's like spinning the top, right? And how hard is it to spin it about the z-axis? So how hard is it? Basically, it's given by this value Iz right here, moment inertia. Okay. Okay. So that's what we want to calculate. Iz, here's the formula that we're going to use it here. So Iz equal to this. So let's use that formula. So Iz equal to x squared plus y squared, and then times delta dv. And delta happen to be 1, so basically this triple integral becomes this one. Okay, so that's what we're going to evaluate. So evaluate this triple integral over the region D. And region D is described by that particular geometry. Okay. So now, up to this formula here, everything is still in Cartesian coordinates, right? Cartesian coordinates. So you will have to actually make a decision from here onwards as what coordinate system that you want to use to evaluate this triple integral. Okay. Whether you want to stick with the Cartesian, or you want to use a cylindrical, or you want to use a spherical, basically. Okay. Yeah. Typically, this one here, proper spherical, will also work, especially if you have a certain boundaries are a part of a spherical surface. Okay, then you should use spherical. But otherwise, this one here, what we'll try is we're going to try to use a cylindrical. Okay. So we're going to use the cylindrical coordinates to evaluate this triple integral. Now you have to jog your mind now. Okay, so if I want to use a cylindrical, then what's the typical procedure? Basically going to have to replace xy with r, theta, z, right? And you're going to also have to replace the dv. If you recall that this is original dx, dy, dz, but you're going to have to replace that with what? R square dr d theta dz, isn't it, right? Yeah. So we need to find basically the limits for z, r, theta. And how do we find that? I said you can literally go through different orders, but usually you actually start from dz first. So usually you start from dz, then dr, d theta. So that should work for 99% of the questions. Okay. Yeah. So your first step is to find the z limits. But in order to find the z limits, actually there's another step you need to do. You need to sketch the shadow of this 3D object in the xy plane. So the shadow basically it's a circle at here. Okay, that's your shadow. Because the shadow, you will use the shadow to find r and theta, right? Then within the shadow, any point within the shadow, you draw an arrow line, okay, across this region D. So draw an arrow line in the z-axis across the region D. First contact give you z mean. Second contact give you the z max. So that's how you find the z mean and z max. Let's try the easy one. The second contact is always on the top surface, so the z max must be always equal to b, right? So z max is always b. Now the z mean, okay, if I look at the z mean is basically falls on where? Z mean falls onto the cone surface at here, right? Falls onto the cone surface. So how do I find the z mean then? So z mean basically it's on the cone surface, which is this. So a times square root x squared plus y squared. That's the cone. Okay, that's the cone here. But we're not using x and y, so we need to replace the x, y with r cosine theta and r sine theta, and that gives us r cosine theta, r squared cosine theta squared r. So that gives us ar at here. Okay. Yeah. So that's your z mean. Is that good? Yeah. Okay. So once you finish the first step now, then you try to find the theta, r, and theta limits using the shadow. And the shadow basically means you draw a arrow lines across the shadow. First contact give you the r mean. Second contact give you the r max. Okay. Yeah. So I guess r mean is quite simple. So R mean is definitely 0, right? What is R max then? Okay, what's R max? R max is the radius of the circle. Okay, yeah, R max is the radius circle. But what's the radius of the circle? Then you have to find the equation for the circle, right? And where is this circle from? It's from the projection of basically the top circle, right? And the top circle comes from where? From the intersection between the top plane and the cone surface. So basically, the top plane is z equal to b. The cone surface is this guy here. So what's the intersection? The intersection basically is what? B equal to this, right? B equal to this. And that gives us x squared plus y squared equal to b over a squared. So which means the radius of the shadow circle, which is R max, so R max equal to b over a. b over a. So that's the interconnection here, right? Yeah, each step R max. Finally, you sweep that reading lines across the whole shadow, which is basically 360 degrees sweep. So that gives you a 0 to 2 pi, right? Yeah. Any questions? Okay. Yes. Yep. So R max is the radius of the bottom circle here. I mean, first of all, when you have a cone and you cut it anywhere across the cone, the cross section will give you a circle, right? Yeah. So this circle here comes from the projection of this one, right? And this top circle is the intersection between the plane and the cone surface. So you let the z equal to z. Basically, you get b equal to this whole thing, right? And which is this one. And then b over a, take a square each side, right? You get the circle radius. Okay. Yeah. Good. So finally, I can set up this triple integral now. So we have a x squared plus here you have x squared plus y squared at here. So that x squared plus y squared will give you the r squared, right? Once you substitute r cosine, r sine into it. This is your x squared plus y squared. And then you have r squared. So you have a dz first, r dr, d theta. Okay. Limits for z goes from 0, goes from how much? A times r to b, and r goes from 0 to b over a, and theta goes from 0 to 2 pi. Okay. I think I tested this question in the final exam maybe 2 years ago. It's exactly the same question. Okay, no change at all. Maybe 30% didn't get it actually. So, any questions on finding the limits set it here? Okay, good. In terms of evaluating this triple integral, I don't think there's any really problem here. So there's actually very straightforward integral, because this just gives you r squared. Okay, and then you can carry out and then end up with pi b to the power of 5, and then 10 times a to the power of 4. So for those of you who are maybe more interested, I think I actually went over this in the previous lecture. How about if you can try a different order of integration. Let's say if you do dr d theta dz, okay, like this kind of order, what will be the limit set here? Okay. If you're going to try, let's say another order, let's say you try d theta dr dz, and then what will be this limit set here? Okay, so give it a try. Okay. You don't have to do this step, okay, but you have to be very comfortable with finding the limits as this one here. Okay. Yeah. Yes. Which one? Like here? Yeah. No, z will be constant. No, r actually, the first one, r would not be a constant. So if you recall that in order to find the r starting from r, right? So you actually will start anywhere along the edge, and then you draw reading lines in the r direction. So r is 0 to this. This is your r max, which is actually, see that equation in here is, this is a z equal to ar, right? So r equal to z over a. Yeah, that's confusing. That's right. So this is why when you change this, this is 0 to z over a at here. Okay. But yeah, you don't have to do this. Yeah, I only found occasionally some students actually choose this order to do. Yeah, somehow. Yeah, very interesting. Back a few years ago, actually, I didn't cover this thing, right? But there's always very few students, maybe a couple of few students, they choose actually to use the different order, and they're able to come up with the right answer. Yeah. So I thought maybe just to point it out here. Yeah. It's more natural to think in terms of z, r, theta, that order. Yeah. Okay. Any questions? Okay. So if no question, that will be it for triple integral. Okay. And then we're going to move on to back to vector fields. So I need to give you a heads up though, huh? From this lecture up to the last one, maybe there will be this 17 up to 22. No, this is how much? What lecture is this one? 19, right? 19 to 23. Maybe five lectures or something. I would say these are most important lectures for this course, okay? Because everything from here up to the end it's an application. It's a mixture of everything you learn, okay? Especially the last week. So, give you a heads up. And don't think that this is the end here. There's actually the highlight is the last lecture of the whole course. Okay. Vector field. What is a vector field here? And what does a vector field look like? First of all, okay, vector field comes from vector function. Okay. So, what's a vector function? We actually already covered that, okay, very much in previous lectures. So let's say if I have a function, vector function, 3 variables, it's definitely going to have 3 components. That's a vector function, right? You know, this is a vector. You plug in a different value x, y, z, and you get different vectors. So that's a vector function. And this is a function in 3D. And we can definitely have a simple one, which is a function in 2D at here. Okay, so that's a function in 2D, and that's a function in 3D. Okay. So you can imagine basically if I plug in different values and I get a different vector. If I plot out the vector in the 3D space or in a 2D space, okay, then we got a whole bunch of vectors, right? Yeah. When you look at the whole bunch of vectors as a whole thing, and that's what we get, the so-called vector field. It's a cluster. It's a field of vectors here. So, for example, right? So I'll show you a few examples of vector field. So, for example, let's say f equal to x I hat plus y j hat. That's a vector function. The first component is just x only. The second component is a y function only, right? Okay. So let's say I'm gonna sketch this vector function. Okay, sketch this out. So how do I sketch this? I will plug in an x, y value into this vector function, right? So maybe let's do this. I'll plug in, let's say, x, y, 1, 1 over here. Okay. So we plug in 1, 1. So for example, if we for 1, 1, we end up with the I hat plus j hat, right? Okay. Now, if you recall, one of the assignments is to practice sketch what? Sketch the greeting vector, right? Greeting vector, or just a sketch of greeting vector here. So, if you look at this vector, I hat plus j hat, so literally you will draw a vector like this, right? So this is 1, this is 1, okay? Yeah. But in order to draw this, you don't actually draw from origin in here. So you really, what you draw here is, you will basically draw the vector, okay, starting from 1, 1, starting from wherever this location is. And then you move that vector here, okay, to this location. So that's the 1, 1, this is the I hat, j hat at 1, 1, okay? Yeah. And you can try again. Let's say if I have -1, -1, and we end up with a negative I hat, negative j hat. So that basically, this is your -1 here. So you have a vector pointing this way, right? And if you have -1, 1, okay, you end up with negative I hat plus j hat. So that should give you a vector this way. And similarly, you have vector this way. Okay. So all the vectors you can extend that back to the origin here. The size of the vector has to be the same as the size of the vector given at here, right? Okay. So now you can imagine if I plug in 2, 2, and I get another vector here, maybe pointing this, but this will be 2i plus 2j. So this is going to be a longer length for the previous one, okay? But it started at, let's say, 2, 2 location, right? Yeah. So if you plot all the possible vectors out, okay, in this here, basically you get, okay, yeah, basically you get a whole bunch of vectors, like an arrow shooting out of the origin at here, okay? Yeah. Now this is basically what we call, it's a field. Okay, this is a vector field. Okay, this is a vector field here. Okay. You got a whole bunch of arrows, okay, flying in this xy plane, but they are going according to the vector function. Okay. So bottom line is, you can literally construct a vector field, okay, for any type of functions here. Okay. So I'll show you a couple things here. So for example, if you have a function which is f equal to y minus yi hat minus xj hat, okay. So this one here, right? Let me And then you get a vector field like that. Okay. So if you look at this vector field, how can we interpret? So basically, it's like there is a small arrows at the center there, right? As it goes to the outer edge, and then you get bigger arrows. Okay. But overall, this field gives you a sense it's doing what? Spinning, right? Yeah, it's spinning. It's a spinning field. And that's actually one thing that we're going to try to interpret. We can always try to interpret a vector field like a flow of waters here. Okay? Sometimes, if you go to the courtyard and then you have this fountain in there, right? But it's actually the opposite of this vector field, because the water flows faster in the center and slower on the outer edge there. Okay? Yeah. You can draw this literally the same way as you draw on the other one. Now, interesting is, if you put a negative sign in front of this vector field at here, then you get a completely different direction of vector field. Okay, different direction. So different direction of flow at here, right? Okay. So this is 3 examples basically for 2D vector fields. 2D vector. We can also have a 3D vector field. So let's say, for example, if you give a function f of x, y equal to c, let's say, for example, x squared plus y squared plus z squared equal to 4, and that's a sphere, right? That's a sphere. Now, if you take a grading vector, so this actually should be the other way around. So if you have x squared plus y squared plus z squared equal to 4, and here's f of x, y, z equal to 4. Now you take a grading vector f, okay? That's what you get, basically 2x, 2y, 2z. Okay? So you got a grading vector, isn't it, right? This grading vector essentially is a vector function. And if you plot this vector function out, and we get, instead of like the planar case, this is a 3D case, you get arrows shooting out in all different directions out of the origin. And the further from the origin, you get a bigger and longer arrows, basically. Okay? Yeah. So this is like basically porcupines, the back of a porcupine is like that, right? Okay. So that's the examples for vector fields, right? Vector fields. Okay. There are many examples for vector fields, and there are many applications you can use vector fields for. Now, this is a very typical example. If you are interested in aerospace, and you probably will design an airfoil, right, for your airplane. Before you actually manufacture it, you want to bring it into a wind tunnel to test this the airfoil. So, how do you test it? You can inject some aerosols into the wind tunnel, and you can actually visualize the flow of the wind, okay, across these boundaries of this airfoil. So that's an example of the flow of the winds across the boundaries at here. Okay. So there you can literally see how the speed changes around the boundaries of the airfoil. Okay. And then you can calculate the so-called the lift force for that shape, for that geometry therefore. And the calculating of the lift, that's actually one of the things we're going to do that right away. It's basically to calculate the so-called line integral of this vector field across the boundary of this geometry. Right? Does that sound familiar? Line integral, right? But this is not the scalar line integral anymore. This is the midterm, right? Scalar line integral. Now this is basically the next part is what we call the vector line integral. Okay, so that's the next topic here. So vector line integral. Okay. So I have a few minutes. I'll just start it, and we may not be able to finish much, but I'll just start this part here. Okay. So I'll start from a very beginning. Okay, it's a very simple case study here. Okay, so let's say that you're learning physics. Okay, you're going to push this block by applying a horizontal force, and push it by a distance of d, right? So then you learned, okay, how much work did you do? Okay, so it's force times distance, or F times d. Okay. Simple. And now this is basically, you're in the high school, that's how you learned. And now you complicate the situation a little bit. Instead of horizontal force, and you apply a force with an angle. Okay? And the angle is a theta. And then you push through the same distance d and here. Okay? And then you're interested in calculating the total work that's done, because you're going to still use the same formula, which is the force times the distance. But the force that here is not a horizontal force, it's an inclined force. So really what you're doing is what? It's the force times how much? The force times cosine theta, right? Force times cosine theta here. And then times d. Okay? And times d. Okay? Okay, so those are high school, right? And now in the university you learn vectors. Then we have to use, you describe the same thing using vector concept. So if I use a vector concept, let's say I use f, okay? Instead of just f, I'll use the vector at here. Instead of d, I'll use the vector representing the displacement, right? The displacement here. So now, if I come back to the same formula here, right? And interesting, how much work basically is done for this same question here? I guess you will write, it's still force times distance, okay? But we will write the whole thing using vector notation, okay? Vector notations. So vector notations basically means it's the absolute value f times cosine theta, and then times the absolute value of d, right? Times the absolute value of d. Okay, rearrange this one in here. Okay, same thing, just rearrange it. And then the last expression in here. What is it? This is what? The f dot d, right? This is basically the f dot d here. Okay. That makes sense? Yeah? And more so, okay, this is f dot d is f dot d hat times the absolute value d here. Okay? Yeah. Right, so vector is always the direction times the distance. So the d is the unit vector, the direction times the distance. So you can use vector notation to describe the total number of work done, okay, for this thing here. So let me finish the general here. So now, if I have a very general question here, let's say if I have a curve C placed inside a vector field. So I don't know how the vector field goes, but it's a field of vector at here, okay? There are a whole bunch of vectors. Okay? Consider that this vector field is a force field. Then if you're going to push an object through this curve C using this force field at here, then what's the total work? Right? What will be the total work done by this force field? And that's what we're going to tackle in the next lecture. Okay? Yeah.